Well, in this problem number 1, we have to classify the equation as ODE, PDE, give the order, and indicate the independent and dependent variable. If the equation is an ODE, we have to determine if it is linear or nonlinear. This equation in part A is a PDE, partial differential equation. There are two partial derivatives of u respect to x and respect to y. So x and y are the independent variable. The dependent variable is u. The order is 2 because that's the highest derivative. That's the highest derivative. In example B, or 1b, we have an ODE. We have only one dependent variable, which is y, and the independent variable is x. Then the order is 3 because that is the highest derivative present. Okay, it is also linear. Why is linear? Because the exponent of the derivative is 1, right? Here we have like an invisible 1 as an exponent, right? So that is why it's linear. And in addition to that is linear because y is multiplying a function of x. So that is why this equation is linear. Okay, don't get confused. This is a 1. This is a 1. Now, part C. In part C, again, we have an ODE, ordinary differential equation, because we have just derivative of y respect to x. Okay, the order is 2 because 2 is the highest derivative. The second derivative, the highest derivative, right? In addition, the dependent variable is y. The independent variable is x. And this equation is nonlinear. Nonlinear. It is nonlinear because we have a derivative. We have a derivative which exponent is 3. Okay, remember this 3 is exponent of the derivative. It's not the order of the derivative, it's the exponent. In addition to that, it is nonlinear because y is multiplying dy dx. So y cannot multiply dy dx. Cannot. In addition to that, it is nonlinear because we have y raised to a power different to 1. Must be just 1. So that is the reason. Example 2. Show that the implicit relationship given by this formula, y is not isolated, is implicit because y is not isolated. Y is not alone. It is a solution of y prime equals to x divided by y. So we need to we need to show that this relationship, this one, which is the given, solve this equation. Well, there are several ways to do this. Okay, notice that the interval in which x is defined is from negative infinity to infinity. So how can you do that? Well, we can find the derivative of, we can start at this equation and then try to obtain the differential equation. So let's find the derivative of the given equation. So if you find the derivative of this given equation, we have 2y, derivative of y squared is 2y times y prime, because remember we have to apply implicit differentiation because the derivative is on y, right? So we have 2y times y prime. Now derivative of the right, derivative of x to the second is 2x, and derivative of 1 is 0, that we don't write. So trying to isolate y prime, we have 2x over 2y, which is equivalent to simply x divided by y. As you see, is the same exact expression we have to arrive at. Example 3. Do the conditions of existence and uniqueness hold for the initial value problem given by these two conditions? So here we have an initial value problem. Remember, initial value problem is given by a differential equation, which is this, and a condition. The condition is y at 0 is -1, and then this condition is equivalent to 0, -1, right? It's the same thing. Now, there is a theorem for existence and uniqueness that states that two conditions should be met for a differential equation to have, I mean, so that the solution exists and the solution is unique. So what conditions are those? Well, first condition is f of x, y equals to dy dx is continuous on a region containing x sub 0, y sub 0, right? And this condition is known as existence. Existence. The condition for uniqueness states that the partial derivative of f respect to y is continuous on x sub 0, y sub 0. And this condition is known as uniqueness. Then we're going to determine if these conditions are met for our example. Okay? Now, In this particular example, f of x comma y is dy dx. And what is dy dx? Dy dx is e to the y minus x times y. So the question is, if we plug the point 0, -1 in this equation, is the equation equation undefined? The answer is no, because if we replace x by 0 and y by -1, then we don't get any undefined expression. So this condition is met. So exists a solution. Okay. Now, trying to find the derivative of f respect to y. If we find the derivative of f respect to y, remember, if we find this partial derivative, then x is going to be like a number, like a constant. So we're going to have what? Derivative of e to the y is going to be simply e to the y. Derivative of x times y is going to be x, because the derivative of y is going to be 1, right? And x is acting now as a number. So the question is this continuous? For or in a region containing this point? In other words, if we replace 0, -1 in this particular expression, is the expression undefined? No, the expression won't be undefined. So there is a unique solution. Okay, so going back to the questions, do the conditions of existence and uniqueness hold for the initial value problem? The answer is yes. Yes. The conditions of existence and uniqueness are met. Okay, remember, if the conditions are not met, you cannot say anything. If the conditions are not met, then maybe the initial value problem has one solution, maybe the initial value problem has no solution, or maybe the initial value problem has no solution at all. So the only thing you can do is check the conditions and see if they met. If they don't met, then if they do not meet, then you do not need to, you cannot say anything. Okay. Example 4. Consider the differential equation 16y dy dx minus 9x equal to 0, which has a one parameter family of implicit solution for every constant c. Okay. So the existence and uniqueness of solution theorem imply the existence and of a unique solution to differential equation that satisfied y at x is 0 equal to 0. Well, let's see. Let's see something. If, for example, we replace, or if this point is given, I mean, this condition is given, y at x sub 0 equal to 0, This condition is equivalent to what? X sub 0, comma 0, right? That's the same thing. The same exact thing. So, the premise. Does the existence and uniqueness theorem imply the existence of a unique solution to this ODE, ordinary differential equation, that satisfied the condition? Well, remember, we have to check continuity of this function, right? dy dx is not isolated in the given problem, right? This is our problem. If we isolate our dy dx, then we're going to have 16y dy dx equals to 9x, right? And then we have dy dx equals to 9x over 16y, right? Now, if we plug this point here, are we going to have any issue? Are we going to have any trouble? Yes, we're going to. Because if you replace x sub 0 comma 0, then the denominator, we're going to have a 0. Now, we cannot have an undefined expression, right? So the answer to this question, does the existence and uniqueness of solution theorem imply the existence of a unique solution to the differential equation that satisfies the condition? The answer is no. Why not? Again, if you replace the point in the equation and now shading in blue, then we're going to have a 0 on the bottom and we cannot have an undefined expression, right? Okay. Part B. Show that when x sub 0 is different to 0, the differential equation can possibly have a solution in a neighborhood of x equals to x sub 0 that satisfies the condition y at x sub 0 equals to 0. Well, this looks like a complex problem. Let's try to work it out. Okay. Well, again, the condition in the problem is y at x sub 0 is equal to 0, which is equivalent to the per x sub 0 comma 0, right? Okay, so our given equation is 16y dy dx minus 9x equal to 0, right? Now, let's replace this point in the given differential equation. We're going to have what? Well, we're going to have 16 times 0, because y is 0, right? Times dy dx minus 9x equal to 0. So we're going to have just, 9x sub 0. So we have 9x sub 0 equal to 0. So x sub 0 is 0. So the problem is forcing to have a value different to 0, right? So it's impossible, because if y takes the value of 0, then x is going to be 0 as well. So this proves that it cannot happen, that there's no way that x sub 0 is different to 0 when y is 0 for this particular equation. Part C. Show that there are two distinct solutions to the differential equation satisfying y at 0 equal to 0. Okay, well, the problem at the beginning states that the family of solution is given by this equation, right? 9x to the second minus 16y squared equals z. So we have 9x squared minus 16y squared equals to z. And then the point is 0, 0, right? This point in yellow is coming from this given condition in the problem. So if you replace x and y equal to 0, then letter C is going to be 0. Then our equation is 9x to the second minus 16y squared equal to 0, right? So let's see. Show that there are two different solutions for this for the given differential equation. Well, trying to isolate y squared, we have negative 16y squared equals to negative 9x squared. Then we divide by negative 16, right? Divide by negative 16. Then we have y squared equals to positive 9 over 16x to the second. And then, trying to isolate y, we apply a square root on both sides, right? So we have y is equals to what? 3 over 4x. Anything missing here? Yes. Whenever you apply square root, we have plus or minus. So we have two different solutions, right? One is positive and the other one is negative. That is why we have two different solutions for this particular condition. Example 5. Find the solution to the initial value problem. Is there any other solution that you can find not from the parameter family of solutions? Okay, so well, the equation is this. Y prime equals to y raised to 2 over 3. And the condition is 0, 0. And then we need to find a family of solution. Family of solution depending on a parameter. And we're going to see what the parameter is. Well, remember, y prime is the same as dy dx, right? So we are going to now isolate, combine all the y's on one side and all the x's on the other side. So we can rewrite it like this. dy over y to 2/3 equals dx, right? And then now we may apply integral on both sides. Keep it in mind that this y2 2 over 3 is the same as y to negative 2 over 3 on the top. Now, what is the integral of y to negative 2 over 3 dy? It's going to be, remember, we need to add a unit to negative 2 over 3. That is going to be negative 2 over 3 plus 1 is going to be y to 1 over 3. And then the integral of dx is simply x. The integral of 1 is 1x plus some constant c, right? Anything missing on the left? Yes. We have this new power, we have to divide by that new power again. So this is equivalent to flipping 1 over 3. We're going to have 3 y to 1 over 3 equals x plus c, right? And then isolating y, we have y to 1 over 3 equals x plus z divided by 3, y equals 2 x plus c divided by 3 to the third. So this is a parameter family of solution. What is the meaning of this parameter word? Parameter means that we're going to have a C in the solution. We're going to have a C in the solution. Okay, C parameter is going to be symbolized by C. Okay, now the condition was 0, 0. If we replace this condition in the equation that we have, 0 equals to 0 plus C divided by 3 squared. Then from here, you can find that C is 0. And then our solution is x to the third divided by 27, because C is 0, right? 3 to the third is 27, x to the third is x to the third. Now, this solution is represented by this graph, this curve. Now, can you kind of guess any other solution that is not coming from this equation? Yes, there is one. And what solution is that one? That solution is y equals to 0. Y is equal to 0. And what solution is that one? That solution is going to be the x-axis, right? The x-axis. This is the x-axis, the same as y equal to 0, right? And then this solution, y equal to 0, does not come from, does not come from this equation. It's not coming from this equation. So we have found another solution that is not originated from the solution we found previously. Okay, so we have two different solutions. Example 6. In example 6, a differential equation is given. dy dx equals to x minus y plus 1. And then we have to determine which of the following is its slope field. How can you find slope field? Well, here we can plot some points. And then determine how the slope is going to look like, given that we plot points, right? We plot points in the given equation. Remember, dy dx is the slope of the tangent line, which is m, right? Now, if, for example, we pick the point 1, comma 1, and we replace it in the given ODE. So if you replace, we replace 1, comma 1, then dy dx is going to be positive, right? Dy dx is going to be positive because we're going to have 1 minus 1 plus 1. That's going to be a positive number. If we, for example, replace, you can replace as any number, any pair. So what about if you replace negative 1, 1? How's it going to be the y dx? Dy dx, if you replace negative 1, comma 1. So how is it going to be if you replace negative 1, comma 1? So we're going to have negative 1 minus 1 plus 1, right? And then that is going to be obviously negative. If we replace, for example, the point negative 1, 7, again, you can replace any pair. So dy dx, which is the slope of the line, dy dx is going to be, we're going to have negative 1 minus 7 plus 1, that's going to be a negative number, right? So if you look to the graph, right? You look to the graph, then it's going to be the graph for 4, fourth graph. Because, for example, when you replace 1, 1, let's find 1, 1. What is 1, 1? 1, 1 is this point, right? 1, 1 is this point. As you can see, this line is having a positive slope, right? What about you replace negative 1, you replace negative 1, 7. You replace negative 1, 7. So let's say this is 1, 2, 3, 4, 5, 6, 7. It's going to be like this, right? So that is why is number 4, number 4, because number 4 is the one showing the behavior of described by the points we plug. Again, you can replace any pair you want. The solution is going to be the same. It's going to be the same. Okay, so part B, sketch likely solutions curve through the additional marked field for the right answer. Well, the solutions are going to be like this. You're going to have this behavior, okay, or this one, okay. And then when x approaches to infinity, to positive infinity, then the solution is going to be described by the green curve, and then the green curve is this one. It's going to be the green curve, right? This one that is already given in the graph. Okay, it's going to be like this. Okay, what can you say about the behavior as x approaches to positive infinity of the solution. Well, yeah, I just did that. It's going to be this green curve. Okay. Okay. Well, uh, example 7. The direction field for this differential equation is shown to the right. Verify the straight line y equals 2 plus and minus 5 over 4x, our solution, provided that x is different to 0. So what do you have to do? What do you have to do? Well, okay, we have to prove that this, change the color, that this equation or this one solve the differential equation, given that the differential equation is this. (25x) over 16y, right? Okay, so I'm going to do y equals to 5 over 4x, and then you can try the other one. Okay, let's find the derivative of this expression in yellow now. So, well, y prime is simply 5 over 4, right? Right? 5 over 4. Now, what about if? How are we going to be sure that these solve the equation? Well, remember, we have dy dx, and then we have 25x, and then on the bottom we can replace, right, 5 over 4x, 5 over 4, right, 5 over 4, because y is 5 over 4x, right? Just replace y by its formula. So we have 16 and 4, you can simplify them. X and the x can be simplified. 5 and 25 can be simplified. So what do you get? Dy dx is 5 over 4. But what is dy dx? Dy dx, remember, is the same as y prime, right? Is the same as y prime. Is the same thing as y prime. Remember, this notation is in Leibniz notation, and this one is in prime notation. But they both represent the same. Now, in part B, we have to sketch the solution curve with initial condition y at 0 equals to -3. Well, so we have this point is equivalent to 0, -3. So what point is 0, -3? 0, -3 is 0, -3 is right here, right? This point is 0, -3. So the solution is going to be like this. I'm going to draw it in red. So the solution is going to have this behavior passing through the point. It's going to be like this. Okay, now we have one more question for this part. Well, no, part D. What can be said about the behavior of the above solution as x approaches to infinity and when x approaches to -infinity? Okay. When x approaches to negative infinity, right? When x approaches to negative infinity, right? Remember, x approaching to negative infinity is this way, right? X approaching to negative infinity is this way, right? So the solution is going to be defined by this line I'm going to reinforce in blue. Okay, so this function, you can extend it, right? So when x approaches to negative infinity, then y is going to approach to what? Uh, y is going to be defined by this line. Okay, and when x approaches to positive infinity, so positive infinity is this way, right? It's going to be this other curve that I'm going to reinforce in different color. Okay, now finally we have to draw the solution for the point 1, -1, right? 1, -1, 1, -1, 1, -1. So the 1, -1, 1, x, y, -1 is right here, right? So the behavior is going to be like this of the solution. It's going to be close to this kind of asymptote. But remember, is there's going to be an open circle. Let me extend this. This is 1, -1. Let's say it's right here, right? So the curve is going to have this behavior. Curve is going to have this behavior through the point 1, -1, and at the x-axis we're going to have a hole. Why are we going to have a hole? Because if you look in the solution, in the order of the problem, you're given a condition that x must be different to 0, right? X must be different to 0. X is different to 0, and that is imposed by the problem, right? Because at x equal to 0, we may have edges. Okay, that is why we have these open circle excluding 0. Okay,